So this is your part 2 video for 3-6 theorems about roots of polynomials. And we have here, what are all the complex roots of the polynomial equation below? Well, first you want to look at your polynomial equation. The highest degree is a 4. So that means that we have to have 4 total complex roots. So we're going to go through and try some synthetic division to try to figure out what some of those possible roots could be. My goal is to whittle this equation down to be something that has a square in it, because once I get down to a square, I can use quadratic formula or completing the square to find the remaining 2 complex roots. So my p is -2. My q is going to be 3. So my p over q's, 2's factors are 1 and 2, 3's factors are 1 and 3. So I have plus minus 1, plus minus 1/3, plus minus 2, and plus minus 2/3. So I have 8 possible roots to go through and test. So let's go try some. 4, 2, -1, -2. Let's say I test 1 first. And you can see I don't even get to the end there, and I know already that's not going to work. So 1 is not a solution. Let's try the -1 before we go through and cross that out completely. So if I do -1, I do get a 0 there. So -1 is one of my solutions. Now I have to find another one, because right now this is 3x to the 3rd plus 1x squared plus 1x minus 2. I need to whittle this down again and find a different real rational root, in order to get it down to be a square. So I'm going to copy these coefficients. I'm not going to go back and use the original coefficients because that's not going to help me, because the original problem was to the 4th power. So I do need to whittle this down. I want to use the 3rd power compressed polynomial rather than the original one, because then that'll let me get down to that square. So normally I would say, well, let's go through and try maybe a 1/3 or a -1/3 or a 2 or a -2, but I already know what the answer is supposed to be here. So to save a little bit of time, I'm going to go through and do 2/3. If you do go through and test some of the other ones and they don't work, just go back and cross them out and go back and try another one. You may have to just cross out your synthetic division and go back to the drawing board. So I'm going to bring down the 3 times 2/3 is 2. I get another 3. Times 2/3 is 2. I get another 3. Times 2/3 is 2, and that's where I get my 0. So this is going to be 3x squared plus 3x plus 3. So my A is going to be 3. My B is going to be 3, and my C is going to be 3, and I'm going to use quadratic formula to finish solving that. So I know I have x equals -1, x equals 2/3. To find the other 2 solutions, I'm going to use quadratic formula. Again, you could do completing the square if you wanted to. Oh, that's not a 1, that should be a 3. 4 times 3 times 3, all over 2 times 3, which is going to be 6. I have -3 plus or minus. We are going to get the square root of -27 here, and that's all over 6. Square root of -27 is going to be 3i square root of 3. All the outside terms can divide by 3, and so that's going to leave me with -1 plus or minus I square root of 3 all over 2. So my roots are x equals 1, x equals 2/3, and x equals -1 plus minus I squared of 3 all over 2. Those are our 4 solutions because it is to the 4th power. This next example I'm actually going to skip through because it says how are the types of zeros of a polynomial function related to the coefficients. We're actually going to skip the investigation of this aspect, and we're going to go right on to the concept, which is the conjugate root theorem. So your conjugate root theorem states that if you have an irrational root as a solution to a polynomial, that means that its complex conjugate pair also has to be a root. For example, if a plus square root of b is a root, then a minus the square root of b has to also be a root. One cannot exist without the other because and notice it does say that you have to have rational coefficients. Because if you multiply a plus square root of b times a minus square root of b, it's no longer irrational. It actually becomes rational. That's one of the reasons why they both have to exist. On the same line of thinking, if you have a plus bi as a root, remember I represents the square root of 1, so it is technically irrational as well, even though irrational is a real number. It is a radical, even though it's in the imaginary number system. A plus bi or a minus bi also has to be a root. So all of those with the square roots, with the i's, they have to exist in pairs. So if they tell you one of them exists, you know that the other one has to exist as well. And we're going to finish up by doing a couple of examples for that. So part A, what is a quadratic function p with rational coefficients in standard form such that we know p of x is equal to 0 has 2 plus 5i as a root? Well, if 2 plus 5i is a root, that means 2 minus 5i also has to be a root. And we're actually going to use the factored form of a quadratic in order to set this up. So remember you had that, the x minus p, x minus q format. Now that p and q is different than the p and q that we just talked about. P and q are actually going to represent your roots. So you're going to have x minus 2 plus 5i, and then x minus 2 minus 5i. And I'm going to have to go through and multiply these together. So first thing I'm going to do is distribute. So I have x minus 2 minus 5i. Well, I'm going to distribute the radical, I guess I should say. And then I'm going to do my regular distributing. Since I have 3 terms in the first parenthesis and 3 terms in the second parenthesis, I'm actually going to have 9 terms before I combine these together. So we have x times x is x squared, x times -2 is -2x, x times 5i is plus 5ix, -2 times x is -2x, -2 times -2 is plus 4, -2 times 5i is minus 10i, -5 times x is -5ix, -5 times -2 is plus 10i, -5i times positive 5i is minus 25i squared. So I have an x squared. I have, as far as regular x terms go, I have a minus 2x and a minus 2x, so that is going to become minus 4x. I have a minus 5ix and a plus 5ix, those add out. I have a minus 10i and a plus 10i, those add out. And then I have a plus 4 And remember this plus 25i squared is equal to negative 1. So this is actually just a plus 25. So I would add the 4 and the 25, and I get 29. And there's my quadratic that has the solutions 2 plus 5i and 2 minus 5i. If you do this correctly, your I terms that aren't squared should all disappear. They should add out. You should have opposite terms so that they don't carry through into your answer. Because it does say it has rational coefficients, and you can't have rational coefficients if you have i's as coefficients in your problem. The next one is very similar. However, there's a lot more multiplying to do because this is degree 4. That means it has to have 4 solutions. So if it tells me 3 minus square root of 7 and I have a 4i, that also means I have to have 3 plus the square root of 7 and a negative 4i. So my polynomial is going to be x minus 3 minus square root of 7, x minus 3 plus the square root of 7, x minus 4i, and then x minus negative 4i, which will actually be a plus 4i. So I am going to distribute the minus so that I have that taken care of. And then I'm going to go through and FOIL. Like we did in the last one, x times x. This will have to stay in parentheses though, because whatever I get, whenever I simplify, I'm going to have to multiply by this one. Because I'm actually going to multiply these last two together, and this one should stick out. This one's a little bit easier to go through and multiply, and you'll see what I mean whenever we get there. So I have x squared minus x squared of 7. I'm sorry, I skipped a 3 there. Again, 3 terms times 3 terms should give me 9 terms. It's one way you can check and make sure you did not make a mistake. Then I have a minus 3x plus 9 plus 3 squared root of 7 plus x squared of 7 minus 3 squared root of 7 minus the square root of 49, which is just going to be 7. Then when I multiply the x minus 4i times the x plus 4i, that's actually a difference of squares. That's going to be x squared plus 16. So that becomes just x squared plus 16. You could do the x squared plus 4xi or 4ix minus 4ix, but the plus and minus with the I terms, they disappear. They add out. So now simplifying, I have x squared minus 6x, my terms that disappear, minus x squared of 7 plus x squared of 7, 3 squared of 7 minus 3 squared of 7. I already did my 2x terms, and then I have the 9 and the negative 7, which gives me a plus 2. And then I'm going to carry down the x squared plus 16. Only thing left to do now is multiply those terms together. So I get x to the 4th plus 16x squared minus 6x to the 3rd plus, minus. Be very careful with your signs. It's easy to mess up. Minus 96x plus 2x squared plus 32. And then combining my like terms, I do have 2 different terms that are squared. So this is going to be x to the 4th minus 6x cubed. I'm going to list this in standard form plus 18x squared minus 96x plus 32. And that is my degree 4 polynomial that has the coefficients, the rational roots, or the complex roots of 3 minus square root of 7 and 4i. There was a lot in this section. That's one of the reasons why this got broken up into 2 different videos. So please make sure you go back and rewatch the first video, rewatch this video. I will try to link some extra Khan Academy practice videos so that you can see this from a different perspective. And reach out to me if you have any questions.